Welcome to the GEOTOP-A seminar. Today's speaker is Oliver Gross from UC San Diego, who's going to tell us about conformal geometry and magnetic relaxation. Take it away, Oliver.
Hey, yes, thank you. It's really great and a pleasure to be part of this seminar series, which I'm really actively following a lot because of interesting topics. And thanks for the invitation to Renzo, who might show up, and for like the introduction here. I said I'm Oliver and just moved to UC San Diego, and I want to speak about conformal geometry and ideal magnetic relaxation, which is a topic that I've tackled together with my collaborators Albert Chern and my PhD advisors Ulrich Pinkall and Peter Schröder. And a motivation for this all is the magnetic relaxation problem, which, put it in my words, is phrased as, if we imagine an electrically conducting fluid, and I think of it as a plasma initially at rest, and if we allow this to relax to some minimum energy state, subject to the ideal MHD equations, we can ask if we can understand this relaxation process or predict the relaxed state. And unfortunately, I won't be able to give like a full answer to this question, but for me, this very simple idea had led to some interesting research directions, which I pursued for a while, and some of which I want to present to you here. So when I say the ideal MHD equations, I speak about the equations of motion for an electrically conducting fluid, and they're essentially the incompressible Euler equations paired with some of Maxwell equations. And that is the continuity equation, which tells us about mass conservation. Then we have the ideal gas law, which relates density and pressure. And then we have the Euler or momentum equation, to which we add the so-called Lorentz force. Since we have this electrically conducting fluid, there's a term more appearing here. And last, we have the induction equation, which tells us how the fluid velocity and the magnetic field are coupled with one another. And this is typically referred to, if you read papers, as the magnetic field is frozen into the fluid. That is, the way the individual field lines in the fluid are interlinked with each other is preserved when the magnetic field is flowing. And a common assumption, if you look into physics, is that the magnetic field is much stronger than the fluid velocity. In which case, we also can neglect fluid velocities and consider these steady states. But since we consider this topology preserving, so the field line topology is preserved during this idea or in these ideal equations, there are still some interesting states for us left to study. And the restricting our attention to these special steady states, the governing equations greatly simplify, and we're only left with this much more simple one equation, which I will refer to as the steady MHD equation. And for this, a rather complete characterization of the structure of generic solutions to this steady MHD equation was given by Arnold, who showed that with some technical assumptions, may put this very vaguely here, they can all be decomposed into finitely many regions, each of which essentially looks like one of the two model domains that I show on the bottom left on right of the slide. There's you either have these interlinked tori on which all of the field lines lie, or these cylinders. And his result basically relies on the observation that this equation already tells us that the gradient on the right-hand side is the level sets of the pressure function. It tells us that the magnetic field is perpendicular to these level sets of the pressure function. And they make exactly up these nested tori, for instance. And again, an assumption is typically made that when you study, for instance, very strong magnetic fields, or such as in the solar corona, for instance, that the magnetic field is much larger than the fluid pressure, and you just neglect the pressure term. So this brings you to the so-called force-free equation here. And the problem here is, in terms of structure, that kind of the term on which Arnold's structure theorem relied on just vanished on the right-hand side. So this is not applicable anymore. And one may ask the question, what structure is still left in this case? And this is basically what got me going here. And there are many interesting examples of these force-free fields, so-called AB FIFO, Hopf vibration in the solar corona, and they also have something to do with creep vector fields. And if you're not convinced by that this is interesting, I hope it convinces you that harmonic fields make up a very special case of them, and harmonic fields are important everywhere. So I believe there is more than good motivation to study what is left here. And okay, so for starters, I want to speak about how I formalize steady MHD equation in a general Riemannian manifold. So the steady MHD solutions are characterized by this force balance between the Lorentz force on the left-hand side and the pressure force on the right-hand side of the equation. However, forces should in general be rather expressed in terms of one forms instead of vectors. We can do so by simply taking a flat. A flat is just inserting it into the Riemannian metric, just in one slot, the vector, and we leave the other one free, then we get a one form. And we can do this, and then we get on the right-hand side the differential, and on the left-hand side, we just get the same term with a flat on top. Okay, that doesn't really help, but after wiggling around the terms on the left-hand side, we can find a more convenient expression which does neither involve a cross product nor a curl. So we got rid of two very inconvenient things for the formulation, which restricts our field of application to the case of R3. But in this case, we really have something more general here. And this is really a one form, so it describes still a force balance in terms of the equality of two forces, that is two one forms. And this is really suitable definition for that, for general dimensions. So basically in the introductory part here, I introduced this little hierarchy of the defining equations. We have the steady MHD equation, then we have the force-free equation, and we have harmonic fields as a special case of that. And now I've written down the definition of steady MHD in a more general setup. And of course, setting the right-hand side to be 0, as the pressure force term gives us a definition for force-free fields. And in particular, harmonic fields we see are again a special case of that, because it's the case of a harmonic one form. So B flat is the one form associated to the vector field B, and the exterior derivative of that vanished, and it's already divergence-free. This I didn't say explicitly, but when I say magnetic field, I already assumed it to be divergence-free, so it's closed and co-closed, hence harmonic one form. This corresponds to harmonic field. Okay, so somehow this definition is consistent with what we like to see. I hope this convinces you. And I want to point out that in the fluid community, force-free fields are also known as Beltrami fields, which indeed is equivalent in three-dimensional setups. But for these higher dimensions, I need to be a little bit more careful, because there's more than one way how you could generalize these ideas. For instance, we've used this idea of a very vanishing Lorentz force as being force-free, but other people think about it as that the defining equation of force-free fields or Beltrami fields tells us that the curl of the vector field B is collinear with the field B itself. And then there's like a proportionality factor in between the two. And this is a valid other definition that we can make for higher dimensions as long as we are in odd dimensional setups. And people do that with good right for that. And to make clear, when we use this definition in terms of the proportionality, I call that a Beltrami field, and force-free fields are the ones coming from the Lorentz force. In 3 dimensions, this is equivalent. In higher dimensional setups, force-free fields are always Beltrami fields, but Beltrami fields are not always force-free fields, but only if they satisfy some additional non-degeneracy assumption. So it's a little bit weaker definition here. Nonetheless, this subtle difference can have like significant consequences for the things that I'm going to address in the talk. which I hopefully point out a little later. And just in terms of equations, clearly by the Hodge star, which relates some k form on an n manifold to some n minus k form, there's an isomorphism between those, we get the equivalent set of defining equations, not in terms of the one form corresponding to the vector field, but in terms of its flux form, which we get from star B, which is called beta here. And I'm not really going to distinguish between the vector field, the one form, and the flux form of it, but just try to keep the equations as concise and readable as possible. But for that sake, we'll switch between those things, just as a little warning. What is now interesting is that there's this hierarchy of the defining equations, and it can actually be obtained as the Euler-Lagrange equations of variational principles, which are distinguished by a corresponding hierarchy of increasingly restrictive constraints. That is, if we only prescribe some flux boundary conditions, we find that stationary points of the L2 norm of the vector field, so of the energy of that vector field, are exact harmonic. If we additionally constrain the de Rham homology class of the field, this gives us general harmonic fields. And if we consider that in the spirit of this ideal magnetic relaxation, we can also put like an isotopy constraints on the variations. That is, we want to find stationary points with that same field line topology. Then we find that stationary fields are force-free fields, and the isotopy constraints in the kind of exterior calculus version, if you write it like that, is just a Lie advection of the flux form. This is why the flux form is very convenient here. We get a very concise expression for that. And finally, dropping the assumption of negligible pressure and leaving the isotopy constraint in place, we find that stationary fields are really steady MHD fields. So this hierarchy relates some interesting classes of vector fields which with each other in a somewhat unified setup. Okay, so much to the physical fields. Now, I've promised to speak about some conformal geometry, and so far I've discussed this hierarchy of special physical fields. And as it turns out, force-free fields are related to another class of vector fields, which are so-called geodesible vector fields. And the question of the geodesibility of vector fields is attributed to Hermann Gluck, who in 1979, I believe, raised the following question that, given a non-vanishing vector field on some manifold, does there exist a Riemannian metric such that the vector field is geodesic with respect to that metric? Okay, and if so, the vector field is called geodesible. And such vector fields are studied, for instance, in the realm of the Seifert conjecture, which states that every non-singular continuous vector field on a free sphere has a closed orbit. And it has been disproven by Kuperberg in 1994. And nowadays, I believe people study it for the more restrictive case of geodesible vector fields, which is why they're interested in having like sufficient conditions for geodesibility. And such sufficient conditions have been given by Hermann Gluck himself and also Dennis Sullivan, who studied the same question in the late 70s and early 80s. And although Sullivan's answer has been somewhat more general, Gluck's theorem is a little bit more instructive for us here. So this is why I'm going to restrict myself to this. And it states that field lines of the vector field X are geodesible if and only if there's one form alpha such that alpha evaluated on the vector field is positive and X is in the kernel of d alpha. And let me give some examples for vector fields which are not geodesible. And these contain, for instance, any vector fields which contain a so-called Reeb annulus. That is a vector field whose integral pairs foliate an annulus in the fashion as I try to kind of indicate on the right. We have an annulus and the vector field foliates it in this way, matching the boundary orientation of the annulus. So to see that it's not geodesible, we can just assume there would be such a one form alpha. Then we can integrate d alpha but since x is in the kernel of it, we get 0. But by Stokes' theorem, we could also integrate over the boundary, which is evaluating x alpha on x in that same orientation. So this must be positive, and this is a contradiction. So it's actually very easy to see that this cannot be the case. So this vector field is really not geodesible. I also want to give a positive example. So in contact geometry, people like to consider these hyperplane distributions, which are maximally non-integrable, and they can be described on odd-dimensional manifolds in terms of a one-form alpha, such that if I wedge it to its exterior derivative wedged n times with itself, we get a volume form. And in particular, this one-form alpha defines as something called read vector field by asking that alpha evaluated on x is equal to 1, and still x is in the kernel of it. So it's transversal to that hyperplane distribution. And just by looking at the definition, how we define the read vector field, we already see that this certainly satisfies the condition that Gluck gave. So these things are geodesible vector fields. And lastly, a little bit closer to these plasma setups or physical field setups, harmonic fields turn out to be geodesible. And to see this, we can go a little bit more general. So for geodesibility, we have these two conditions that we want to see satisfied. And if we start out with a Riemannian manifold and a non-vanishing vector field on it, we can do the following. We can just define the vector field x that we want to find, or x as b, and the one form alpha as the flat of it. Because we have a Riemannian metric, we can do that. We can take the flat, but if we write that down, we actually see that this exactly matches the force-free condition, right? This is the defining equation for force-freeness. And the left-hand side, this evaluation greater to 0, just simply means it doesn't vanish. It's just the squared norm of the vector field itself. So from this simple argument, we find that force-free fields are geodesible on their support. And the converse is also true, although it's not as easy to see. And with force-free fields being harmonic fields being a special case of force-free fields, they are also geodesible. So this hopefully convinces us of that. So this resolves the claim I've just made a minute ago that harmonic fields are actually also a positive example for geodesibility. And this hopefully gets you into the mood and understanding why I addressed this problem of geodesibility. But you might ask the question, okay, force-freeness is defined with respect to a metric. So to define force-freeness, I need an ambient metric for that. Same with harmonic, like your harmonic with respect to some metric. And the same holds true for geodesibility. There exists a metric h such that. And the problem here might be that g and h are not in any relation whatsoever. I have some topological manifold and I equip it with one metric and then I change very different arbitrary metric. And this makes it geodesible. So this is actually not so exciting. It's a very topological statement, of course, and this was the original motivation for Gluck to study this, to find the topological obstructions of the field lines. But one can still ask, can we do better? And it turns out we can. And it turns out that force-free fields are geodesible in a conformal, are conformally geodesible. So that is, the vector field is force-free with respect to a metric G, if and only if its field lines trace out geodesics with respect to a conformally changed metric G tilde. So a conformal change of metric is just multiplying the metric with some positive scalar. So it's a pointwise rescaling, which changes the way we measure length, but not the way we measure angles. And this is a result that we've shown a little bit recently, or not so recently anymore by now. And the interesting part is that we can not only show that there exists a conformal change of metric, but we can give the conformal change of metric very explicitly. It's the squared norm of the vector field as measured in the first metric that we start out with. There's also formulas to make the converse step and express everything in terms of the metric G tilde that we get, but the formulas look more ugly. So I only state that one way. And what this reminds me of is that, so it's kind of interesting that the conformal change of metric that we need to make these force-free fields geodesic actually depends on the norm of the vector field itself. And this reminds me of these cases that we see in other places in physics, like in general relativity, where particle traveling on a geodesic trajectory in a space, on a metric on a space that it warps around itself with a mass, right? The mass of the particle affects the space in the metric, and it still travels on a geodesic. And the same holds true for like minimal surfaces that are minimal or harmonic functions we get with respect to some metric. And if you want to compute them, you typically use this idea of, okay, you solve for harmonic function, then you get a new like triangle mesh in the computer, then you compute a new metric for that, the new Laplacian, you solve again, and you iterate this procedure. Turns out you converge to minimal surface. This is like the most simple algorithm how you typically compute these things. So these are also instances where kind of this interesting property depends on the metric that the thing itself generates. And I believe this is interesting. At least this was very striking to me. And I want to give some examples for what this tells us. For instance, the ABC flow is a very popular example for Beltrami flow or Beltrami field on the free torus. And a corollary of this theorem tells us that Beltrami fields are conformally geodesic. And this is interesting because typically these are studied for their chaotic field line behavior for generic choices of the parameters A, B, and C. And what the theorem tells us is by locally rescaling the three torus or the metric on the three torus, we get something chaotic to be a geodesic foliation. So this is from being very chaotic to being, I believe, pretty much very much in order. I believe the geodesic foliation is pretty much a very ordered thing in some sense. So this is interesting to me that this happens just by rescaling. Moreover, if the field has unit norm, then it's force-free if and only if it's geodesic. And example for this would be the Hopf vector field on the 3 sphere, which I show here, the Hopf vibration of R3, its stereographic projection. Since it comes from great circles, we already knew it was geodesic. But now we also know that since it has unit norm, it must be that this is a force-free vector field, even with respect to the same metric. So no change of metric needed. And having this particular conformal change of metric and knowing what we're looking for, you can actually make a little bit of a stronger statement and relate all those variational principles with each other. So it turns out that just by applying a conformal change of metric, stationary points of the L2 norm will correspond to stationary points of the L1 norm after conformal change of metric with the same constraints and boundary conditions. So you can really relate this hierarchy of force-free fields, harmonic fields, exact harmonic fields to something like geodesic fields, iconal fields, and exact iconal fields. And what this looks like in the variational field is like this. So we have a 2 norm and a 1 norm, and we take the same constraints and boundary conditions on the left. And just by the conformal change of metric, you can either do the variational calculus with respect to that new metric, or you can just check that after transforming the Euler-Lagrange equation, you will immediately get the Euler-Lagrange equations for the other one. Because all these quantities, like the flux form, the field, the volume form, we know how they transform under conformal change of metric. So there's many ways how you can prove such a result. And I feel this relation between stationary points of variational principles by conformal change of metric is an interesting result here. And later, I hopefully will show how to make use of that. So what we did here is kind of the geodesibility of vector fields for force-free fields was known. Like Gluck and Sullivan, they all knew that already. What we added here is that we actually showed that force-free fields are in the class of conformally geodesible vector fields, which to the best of my knowledge, only Killing fields were so far known to be in that class. So we showed that. And in particular, as it turns out, this is a strong statement because if you would have taken a different turn in the beginning and defined your generalization as being a Beltrami field in terms of this collinearity condition, it turns out that I believe Robert Cardona or Daniel Peralta Salas, around those people, they gave results that I think it was Cardona, in any homology class, in any field, there's like volume preserving Beltrami fields, which are not geodesible. So with just having this additional regularity, switching to the force-free condition instead of the Beltrami condition, we get a much stronger statement instead of things breaking apart. So this is maybe a good place to ask if there's any preliminary questions so far. Okay.
Oliver, I have a question.
Yes.
Renzo here. I was very surprised to hear that the Hopf vibration is a case of a force-free field. And I wonder
Yes.
if you, on the basis of your, on the structure that you have investigated, you can immediately say something about stability.
No, I don't know anything about stability. What I know is that it really seems to be a point where things spin. So there's work by Christopher Berg-Smeed. I think you know him as well. He mentioned he's at EPFL in the plasma physics lab, and he did in his thesis work also relaxation of the Hopf vibration, and found that this is really a force-free field, and it seemed to relax to a stable point. And then I think, or I believe, might be not super correct here. I believe he kind of studied how the field line structure changes if you then start to inject pressure and not neglect it all the way, how things change in that regard. Something like that I have in my mind. But I
And
have
then
no direct result on stability.
If I may, I have still another little curiosity. Your consideration of Riemannian manifolds is related. I'm sorry, of course, I like very much the extension to which you went to consider all these conditions. But I wonder if you have any new features in terms of physics or in terms of your relaxation method that you're going to consider when you go to Riemannian case and these generalizations. I mean, it's just a matter of classifying properties.
Yes. So the only thing more general that you get from it is that what I haven't written in the paper is, but I know it's true, that you can do this in a more general setup. So you can also describe, for instance, minimal surface using something called calibration, which is exactly like the iconal case that corresponds to field lines. If you not consider a flux form, but like in co-dimension 2 thing, then in 3 dimensions, you get a minimal surface. And this is the same condition here. And what is interesting to me is that what typically is considered in this calibrated geometry setup is kind of the closed forms that calibrate something. So this is the harmonic case, so to say, in the plasma setup. But the plasma setup gives us a nice idea what a more general equation of that would be, which is still geodesic in the field line case. So it's still a very reasonable equation, but much more general because we allow for these twisted cases. And there's no kind of reasonable twisted generalization in R3, but you could consider these minimal surfaces in R4. There you have enough codimension to consider the twist, kind of what would be the force-free case or the PDE that describes to you the corresponding thing for force-free fields in the surface case. And I can write that down. And this is something that is still on my list that should be investigated maybe at some time, because you could still graphically project and get something like a twisted minimal surface. I'm not even sure if that makes sense or if these things are integrable or are reasonable surfaces, but just in a distribution sense, that makes sense. And I can write down the PDE from that physics motivation. And I have some hopes that maybe something will fall out of knowing this generalization of what would be a good generalization for a calibration, because calibrations pop up all over the place. And I believe this might be something if that
Thank you.
goes into that direction. Okay. Okay, cool. So I promised actually not to bug you with geodesibility or this somewhat made up question of geodesibility here, but I was to speak about ideal magnetic relaxation. And just from the insights that we got now, that all three fields are conformally geodesible, and these fields somehow make sense. I hope this gives some motivation for the following. So, like, put very simple, my understanding of ideal magnetic relaxation is if I take a bunch of field lines, I tie them in a knot or put like a simple link, I close them up and let them go, what happens? Okay, and by the induction equation, we know, okay, the field line topology stays where it is, or stays the way it is. And then I read a paper by Moffat, who had this idea, or who presented this idea that, okay, if I have the magnetic energy, there's this, I believe it's called Arnold inequality, which tells us that it's bounded from below by the helicity of the field, which is basically just the way the field is knotted or linked, or if that is non-trivial in any way, we have a lower bound. Okay, so if the field is not super boring, there is something like that. And then the idea is, okay, if we now can consider something like the L2 gradient flow that is still leaves the topology preserved, move everything by a diffeomorphism, so to say, and reduce the energy, there should be a limit, right? This is the simple idea here. And this actually got me going on all of this. I found this a very striking idea here. And okay, let's consider a setup how we can think about this. So we can kind of build this discrete version of ideal plasma by decomposing like R3. Now we can just R3 into several regions, some of which have some magnetic field on it, some of which do not. But we want to consider everything in weak sense. So there might be these current sheet surfaces in between where things meet, where we have discontinuities in the field. That doesn't hurt. And we can still consider a corresponding variational energy. And if we consider an ideal relaxation, then kind of corresponds to this isotopy constrained L2 gradient flow. And you can show that stationary points of this energy under isotopy constrained variations actually satisfy the steady MHD condition. And then you have some pressure continuity conditions, of course, for these weak solutions, but this all kind of makes sense. I don't want to go into like much detail here. This has been, I believe, worked out many times. But having this, we figured out a way how to use this to describe these plasma regions as a continuous set in terms of the field lines. So we just bundle a bunch of field lines together so that they all have the same flux. And then we can use this idea to actually come up with a discrete version of that energy and represent the field by a finite set of curves with thickness. So we have these cubes representing the field. And I claim this is a reasonable discretization of the whole ideal plasma idea. And to compute stationary solutions, we want to minimize this idea. And here, an idea I had a while ago is that, okay, if I look at this, this is actually just a sum over all these field lines, and I integrate over the length this integrand. And this integrand is something positive, you can show that, times the Euclidean length element. So I can interpret this as the length element of a conformally changed metric. And if I do this, then it's actually just this energy corresponds to the sum of length of the filaments just measured in a different metric. That is, if I want to do this ideal relaxation, I just need to do an isotopy constraint L1 gradient flow. I want to make curves shorter. If the energy is the sum of the lengths of the curves, making curves shorter is a good idea. Then this helps minimize it. So this leads to a very simple optimization algorithm. I just first need to compute the metric and then perform a curve shortening step. But curve shortening steps in a conformally changed metric is very well studied, and we know how to do that. And then I only need to recompute the metric. And I just iterate these two things until I get some type of convergence. Okay, and on the right, you see what this looks like. And I want to emphasize here that this non-overlap constraint somehow is built into the metric by assigning some of material properties to these plasma filaments. So electromagnetic interactions, as it would be in the plasma case, is actually described in terms of something like a mechanical interaction. And it's all built into that conformal change of metrics so that there's no constraint on this optimization. It's really just a pure unconstrained optimization, just a gradient flow on this. And everything else happens by itself. And to understand this, we can decompose this integrand a little bit and look at it a little bit closer. So we have these two factors. One is some factor that accounts for the ambient pressure, which we can just think of it as constant. So this is a constant scaling of everything. We don't really care about this. But the second part is actually interesting and tells us something. Decomposing this, we actually find that this factor measures something like the field strength of the filament, again, or the deviation of the field strength of the filament, as opposed to or from a optimal field strength that the filament would like to have given its flux and the ambient pressure. So if I just put a filament not near to any other filament, it will be confined by some ambient pressure and have something like an ideal thickness, but due to a constant flux, the thickness is proportional, inverse proportional to the field strength. Okay, so actually this measures, let me say, how happy the filaments are. So whenever a filament is unhappy, this term will grow. And this makes the metric, all right, I'm getting ahead of myself here. Okay, maybe let's do this step by step. So the filament strength is inverse proportional to the radius of this tube. This is because of constant flux. If I now put a second tube close by, they need to shrink because they're not supposed to overlap. So each of them can have at most a smaller radius. But this is a deviation from the radius or the field strength that they would be happy with. So this factor actually becomes larger. And a larger factor means it's more expensive for the curve to pass this specific point in space. So in the following curve shortening step, these things will actually move away from that last conformal, from that region with a large conformal factor to regions with a smaller conformal factor, because it's cheaper to go that way. But then they can also relax their thickness again a little bit. And what we see is kind of the equilibrium between taking a detour and being squeezed together. This is what the equilibrium will tell us in the end. And so this is the paper of Moffat that got me very intrigued because he proposed to relax a flux tube in the shape of a knot. And he raised some interesting questions that it's not clear like how a T32 knot would relax to a T23 knot just by doing this ideal relaxation idea. And with a discrete setup, we don't need to have a lot of filaments, but we have a very small set of filaments that we can have interacting. And this idea in terms of like representing these plasma knots as curves with thickness has already been studied even by Renzo. And it shares similarities with the problem of finding the rope length of tight knots, because both of these things require some shrinking with a non-overlap constraint. In effect, these rope length algorithms have been used to study plasma knots as well, in a sense. But I claim that kind of the equilibrium here, we see that it exhibits a non-uniform thickness. The thickness is somewhat color-coded on top of that center curve here to give you an idea. So actually, we need to account for the, let me say, squishiness of these plasma knots as opposed to these idealized ropes that are studied in the rope length problem. And this is typically numerically challenging. How should we encode for this force pressure pressing out when this filament is squeezed together? And I believe this geometric idea is somewhat an elegant way how to do with that, because it's all encoded in the metric, and the metric tells us how things are pushing apart and so on. So this is kind of a nice way to find these natural embeddings of knots and links in yet another setup. I mean, there's no good answer to the question, what's the best embedding for this, but it relies only on local geometry optimization. Under some technical assumptions, we can make sure that it's isotopy constraints, and it accounts, to my knowledge, for the first time for this elasticity of these magnetic flux tubes. And so this is, I believe, an interesting idea, and I hope you find this interesting. So if you take anything home from what I've told you today, is that there are these physical vector fields and there are geodesible vector fields, and people have found that force-free fields are actually contained in both of them in this Venn diagram. And what we've added to this is this idea of conformal geometry, that it's actually an intersection of the three of them for this case of force-free fields. And motivated by this idea, we can kind of spin off ideas for how to perform like very discrete ideal magnetic relaxation of these plasma knot slings and tubes. And for instance, study these questions raised by how does the T32 flow to a T23 knot through this type of progress. And this is so a geometric interpretation of this magnetic relaxation problem in terms of conformal geometry, which is hopefully what I promised in the talk title in the abstract. Pretty much everything that I've told you is kind of written down in these two papers that I published, and pretty much is the core of my PhD thesis, which I just recently defended last year. So if you're interested in any of that, feel free to read that or reach out. And with that, I thank you for the attention and the invitation.
Thank you. Thank you very much, Oliver. Great, interesting, very interesting talk for me, and I hope for our audience. So first thing is, any questions from who has attended this lecture?
Oh, sorry. Go back
I
here.
hear some sound. Anybody?
Yeah, Oliver, I have a question. For those thick
Oh.
knots and that you get as in the relaxed state, are they unique?
You mean in terms, what do you mean in terms of uniqueness? Are there several local minima you're asking?
Yes. So
Can I get stuck in minima? Yeah, it's very likely that I get stuck in minima. I have the same, pretty much the same struggle that all the rope length algorithms have so far. Depends very much on the initialization. I was able to relax like this pair compare to the same state, which I took as like good validation that at least somewhat works. But since the optimization in my implementation as I do it right now is purely local, because I need that to make sure that I keep in the same isotopy class. I cannot like do good global line searches for stepping. This is very prone to getting stuck in local minima, I believe.
Yeah, yeah. Thank you.
Yeah, this is.
Oliver, maybe I missed, or I don't remember. I heard you saying anything about just basic constraint on the volume, magnetic volume, and on the cross section. Can you say something on that?
I mean, you can do the same thing like volume just by rescaling everything by volume preserving. Currently, I don't pay attention to that. So I know that you asked me in Karstadt already that I should do some experiments to really kind of satisfy all these things to get or kind of normalize everything to get an idea of what is really the spectrum of a magnetic knot of these plasma knots, to really compare their spectrum numerically and compute this a little bit more carefully. I haven't gotten to that yet, if that is your question.
Relationship with rope length. I found rope length a wonderful way to discriminate energy in the relaxed state, and that's kind of related to the question of constraining relaxation under volume or other quantities. The cross section, however, is kept, so to speak, circular. Is that correct?
Yes. Oh, yes. Yeah. That is circular. I mean, that certainly also gives you errors, right? This is a very crude approximation. Although I know there is work by physicists, I came across like De Forest and Kankelborg, something like those names. They call these a very similar idea on these on kind of relaxation on curves. And they use Voronoi cells as cross-section diagrams, but they are in the solar community. And they call these fluxons as kind of the similar to a voxel or a pixel. They call it a fluxon as kind of the discrete primitive that you have. So you could go about and kind of go further and compute a Voronoi cell and basically make the same deduction here. But I never found this.
Is that correct?
too
I mean,
appealing.
numerically speaking, you have a polygonal structure that is edge with another one, and so to establish a minimum under small fluctuations is extremely challenging, I believe.
Yes, yes. They also, I mean, they have the better way of saying they account better for the way things are interacting with each other in terms of they try to fill all the gaps that I have with my circular cross sections. But they also come to approximations that they cannot really approximate the field density, and they get larger regions. And actually, the larger your cross-section area, the more crude your approximation of this idea. So how you get from fixed flux and the cross-section area to an approximation of the magnetic field strength, which is what you're actually after, is by assuming, okay, we have an untwisted field in that flux tube, so I cannot model any twist along the filament. This is also something that I'm still trying to understand. How would that play a role here? If I assume I have a twisted field inside, how does that affect kind of the relaxation direction that the filament wants to go in that geometric picture? This is, at least I don't make good progress with that, let me say. It's a hard question to tackle, or I'm just not capable, but there's like a lot of crude approximations here that you assume it's untwisted and it's approximately constant over the cross section, and only that gives you an approximation of what the field strength actually is. What I believe might be a good idea is just to make the computation more efficient, because currently the problem that you have numerically in my setup is that you need to have, for conformal curve shortening flow, you need to know the gradient of the logarithmic conformal factor. And how to get there, because I only know the field strength on the curve itself. I don't know it on open sets, right? This is problematic. And how I currently do it is I make basically a neighborhood search for each vertex, find the k nearest neighbors, and take finite difference average of that as an approximation of the gradient. And it seems to do a good job, but this takes like 98% or 90% of the computation time in the implementation right now. What I believe would be a much smarter move would kind of use these, put a background grid, extrapolate it from that, have a gradient computation on the grid, which is much more efficient, and then put it back on the curves itself. So kind of going back and forth, which I see frequently done in like these graphics realms. That people do that for like Lagrangian fluid simulations, that they have these Lagrangian or Eulerian mixed methods. I believe something like that should be done, and there's many ways to improve the implementation before trying to get to real kind of numerical experiments in terms of classifying or getting really approximations for the energy and trying to understand the spectrum of these things. I believe one first needs a more trustworthy implementation of that. Or
I
more
have
elegant.
another.
Yeah.
I find your talk extremely fascinating. Well, there is the big problem of circle packing into 3D, so the tube packing might be even much higher complexity to consider. I'm thinking of the cusps of a void that you have to somehow measure. But moving to something else, there is a growing interest in relationship between knots and or links and chirality. Have you considered relaxation of say a left-hand trefoil and the right-hand trefoil? Can you say anything about that?
No, I never looked at that. Do you
I
believe
suggest
this
to
would
do
be
it because,
interesting? What would you expect? Like
well,
that
my
is
point,
that they have.
I have a very naive
Uh-huh.
answer that might be totally wrong. So if you do not consider twist,
Mhm.
then I would be very surprised to see a different energy level in a link of a left-handed, right-handed trefoil tube.
Oh yeah, for twist, I certainly believe that there might be, yeah. But
Okay,
this I
if you
cannot,
insert twist,
yeah,
then is a different story, and it makes
yeah.
I think the problem extremely interesting. But if there is
Yes.
no twist, then I don't see any reason why the two knots would have a different energy level than just a link of two same-handed trefoils.
Yes, I would certainly agree with that. Yeah, I believe kind of extending them. I really like the ideas, but it has two big weaknesses. I cannot do twist, and this feels somewhat reachable or like fixable, but I'm not making good progress. But I believe there must be something. And also the question of whenever I speak to like the people really from the plasma community, they ask me for this Taylor relaxation. They want to see reconnection happening, but you don't want to see any type of reconnection, but you want to see this helicity preserving reconnection, because otherwise you just relax to harmonic fields, just solve for harmonic fields all along. Okay, but this Taylor relaxation is much more complicated. And so I believe one should kind of try to understand what this means in terms of how to say, maybe something like, first of all, this should be rephrased in terms of a level set method. But there are these level set methods which evolve curves and do curve shortening, flow in these things, evolving complex valued functions on R3, so that the curve is represented by the zero set of that function. And this handles reconnection very well. And these are very nice methods. And already having a complex function gives you some notion of frame along the curve. So I believe this is a setup that could potentially handle this idea of a twist in it. I just need to figure out what would be the gradient direction for that. That is still doable. The problem here is how to constrain this reconnection, because these things really want to reconnect, how to constrain it to this helicity preserving set. So is this some type of a co-adjoint orbit? Is there some group action so that I can describe that? I'm puzzled about that. I really don't know. But this is something that I try to look out for, because I believe this would be the correct formulation to tackle this. And you could still leverage this idea of a conformal curve shortening flow, which would be likely very nice to have. Because I believe typically the physicists want to have like really a field structure relaxing. But I like this idea of having this very discrete set, of having one primitive, one curve, or a sparse set of curves, and see what happens there. If we look at their reconnection, maybe we can understand what happens on a field level. Like I believe having these discrete primitives has some benefit. So this is kind of my thoughts in that direction, but all very vague and maybe just plainly wrong. I don't know.
I see Mitch Berger in the audience. Maybe, Mitch, you want to comment on Taylor's context, so to
Yes.
speak?
Well, I have one comment. Just numerical simulations where you allow reconnection and there's high enough conductivity to almost preserve helicity. You don't seem to get to all the way through Taylor relaxation in many circumstances. Instead, you get one region of positive helicity and one region of negative helicity. They seem to separate, and it would be interesting to know geometrically exactly when this happens. I mean, you can see it intuitively if you have two parallel flux tubes that are oppositely twisted. The field lines line up, are pointing in the same direction where the two flux tubes touch each other. So they don't want to reconnect. Whereas if the two flux tubes are the same sign, then they will want to reconnect. So there are big things like that which come out of the numerics, but I haven't
Yeah.
seen much coming out of the pure maths.
is there some conjecture that this is kind of the case that this happens, that there's also some type of topological obstruction in the field that you start out with that doesn't allow it to get there? Kind of as in geodesibility, you have this topological obstructions coming from like non-trivial tangent homologies, and for this case, there might be some really obstruction in the field topology that it doesn't work.
There might be, yes, yeah. But
interesting. Yeah, so while you're here, can I ask a question? I mean, this is maybe unorthodox, but so I have this hierarchy of variational principles, and everything seems to work out pretty much perfectly, and it's a very beautiful picture from my point of view. But I can't make Taylor relaxation fit because it's a different setup. It doesn't come like the helicity constraint is typically put in a way that you like add a Lagrange multiplier and then go from there. And you get these, so actually in this hierarchy, you typically have, you have force-free fields, then the linear force-free fields, then harmonic, then exact harmonic fields. So you could go one step more, but I can't make these linear force-free fields match the setup that I can say I get the variational principle from a constraint on the setup. So it feels to me like this is a very different setup in some way because it doesn't match the rest of the things I see, which all work out beautifully. Why is that? Or do you have any idea how this could be fixed, how to make this work once I show you this?
I just have one or two vague ideas, which may not even be relevant, but one is just a field that's sort of, you're allowing current sheets, so it's finite except for current sheets. The other thing, I wanted to make a comment on this before, that might be related to some of these questions. So in the middle of your talk, there were things you were doing where you would sort of take out the magnetic field strength, keep the field line shapes, but there were things where you factor out the field strength. And recently, a number of people have been working on something called field line helicity, where you do much the same thing. Instead of magnetic helicity, where you integrate linking number times d flux 1, d flux 2, basically. You don't weight by flux, you just weight by dx1 squared, dx2 squared, whatever. So you're taking out the field strength and getting sort of this sum of all the linking numbers or twist numbers. And I don't know whether anybody's ever put that sort of thing in a variational principle or really, touch with it.
But what was the name? You said field line helicity, right? I'm going to note that
Field
down. That
line
sounds interesting.
helicity. Yeah.
Let me just note that down. Okay, yeah, I just wanted to ask, well, while I have this audience here, I can use the time to ask a question myself.
That's perfectly okay. That's the purpose of meeting and having these webinars.
Yeah, so this work is all far from being done, I think. Oh, sorry, I didn't mean to interrupt.
Okay, thank you very much for... No, not a problem. I think Oliver, wonderful talk. Thank you. Thank you so much.